So on behalf of the SAICE Academy, I'd like to welcome all of those online to this virtual site. We are sitting in the GIB offices in Westville. Obviously, we are not on the site. The site is quite remote, as you will soon see when Duncan and Gordon do their presentations. So from a SAICE Academy perspective, I'd like to obviously thank GIB for collaborating with us in terms of doing the site visit. The client for the project is Umkhomazi Water. We also have with us in the venue the construction manager for Step Stocks, or the consortium, which is Esmond Robertson, and our presenters today is going to be Duncan Shaw and Gordon Druce. Duncan's going to handle the technical aspects. I'm not sure whether he filled the short straw or whether he did the technical stuff. And Gordon's then going to give us as much of an insight on the actual site as what he can, using various drone footages and other things. Both Gordon and Duncan have asked if you have questions while they are presenting, please feel free to pop them into the chat, and between Oliver and I, we will monitor, and they are more than happy to answer questions as we progress rather than at the end. So you are not interrupting them. I think in terms of getting a better understanding of the project, if it's Duncan glibs over something too fast and you want to ask questions, then please feel free to do so. And from that point of view, I'm going to now hand over to Duncan and Gordon to take you through the project and obviously to show us the work that is being done on site. So thanks everybody for joining. Don't forget you need to stay in for the full session to get your number of hours in the session for CPD, and over to the technical team from GIB. Thank you, Duncan and Gordon.
Sorry guys, can I?
Yes,
we do have a hand up already. Sorry, Umkhomazi, his hand is up. I'm not too sure if he wants to ask a question. Not too sure what the question will be, but his hand is up. I don't know if it's a.
Okay, hold on a second.
Nonko?
Now they can't talk, Oliver. I've got to just enable the mic.
Okay.
Okay, Nonko, you can go ahead.
Nonko?
Maybe they're waving hello. I'm not sure.
Yeah, maybe Tom. Okay, let's leave it then. Thanks.
Okay, let's get on with it. We'll come back to the hand if we need to just now. Thanks, Ollie. Right, over to you, Duncan.
Okay, welcome everybody. So just to start off with the slight in that the client is not Umkhomazi Water. It's now Utkela. Sorry, this is the share screen. What do you say? Nothing.
We're just getting the presentation so that you can all see it. Ollie, you are our pointsman on that.
Not a problem, Tom. Yep, something's coming up. We've got your low Umkhomazi bulk water supply scheme. I think we're good to go. I can certainly see it.
Right. Okay. Right.
And presentation is up, Tom.
Good. So just to start off with the Umkhomazi name change to Umkhomazi Utkela. That's very important. So what we're talking about is the lower Umkhomazi bulk water scheme, not to be confused with the up-and-coming upper Umkhomazi scheme, which everybody's been hearing about for decades, with dams on the Umkhomazi and what have you. This is right by the coast, and it is by the south coast, Durban south coast. So I'll be giving a presentation just to put the whole thing in context, what the whole scheme's about. Most of the site visits for one of the particular contracts, which is the good enough extraction and pumping works, which takes water out of the river and would send it on its way to the works. So it's important to help just get the thing into context. So most people would know that the Umkhomazi system that supplies Durban-Maritzburg corridor is quite under stress. as far as it goes, pushes north as far as Belito, and you have the lower together scheme, Mandini pushing south towards Belito from other side. But on the south side of Durban, there's only Amanzimtoti waterworks and there's Mzinto waterworks, which are pretty small in terms of looking at the big picture supplying the whole coast. So for a long time now, Ugu has been battling water, and Itiquini, we have the Agani particular have the South Coast system. The South Coast pipeline was built some time ago to take water down from the Ngani system, feed it south past Durban down the coast as far as Scottsboro and the like. This now needs to be augmented. So the only other source of water is the Umkhomazi River, which at the moment is unregulated. When the upper Umkhomazi comes online, it will be utilized from higher up. So this is not.
Sorry,
Yes,
sorry, I
Oliver.
don't mean to be rude. There's a couple of comments coming through that the presenter's a bit quiet. We're not sure if it's just the distance he's away from the mic or whether there's a volume.
We've got a conference mic, so let's just check if we can turn the volume up a bit more. Are you hearing okay?
It's I can hear it, but it's not kind of like you and I are talking at the moment.
Okay.
So it is in the distance. I don't know if the mic could get closer to them.
Okay, we're fiddling. Yeah.
Okay, testing. Can you? Is it loud enough now?
It's a little bit better. Okay, we're getting some thumbs up. I think we're good.
Okay, good. It's less worse. All right. I thought I had a projecting voice, but I'll just sit a little bit closer. So we're saying that this whole lower Umkhomazi scheme is to augment the south coast, and all the feasibility studies were done back in 2015, 2016 by ACOM. They finished their studies and then went out to procurement to do the detailed design, which goes to another consultant, GIB and our CPG partners. The was conceived as supplying 100 megalitres a day. The actual design of the waterworks is based on a maximum delivery of 130 megalitres a day. That's the general scheme. Let me put in context where it is. So those who are not in KZN, it's about 20 km south of Durban, Umkhomazi area. There's the waterworks going to be based at Craigieburn, which is very close to the freeway. It's the one red dot. It's called Good Enough. You'll see on the screen. You'll see another red dot called Umkhomazi. We'll go on to explain that. That would be to augment the raw water in dry river months. So the three distinct components.
Tom, we've lost volume on their side.
It's too dry. There's not enough to extract. Then water will be released from that dam. So that's a totally separate. And has nothing to do with the waterworks. The other one is another abstraction works at Good Enough, a place called Good Enough. The original farm where this is based was owned by a chap called Good Enough. And then there's the Craigieburn Waterworks and clear water conveyance and storage. So the raw water side has been by our CPG. The clear water component has been undertaken by Ingerop V3 joint venture together with their CPG partners. So we'll be talking about the raw water side. The schematic helps you put the thing further into context. So on the left, you can see extraction works, pumping directly into off-channel storage dam, and then gets released in winter. The middle bit is the good enough one, which we're looking at today, where again we pump from the river. This time where you'll see a silo with a twirl on it. That's supposed to be a hydrocyclone. Then goes to the balancing tank in the heart of the pump station. Goes up to raw water storage reservoirs at 12 hours storage, and then gravitates to the waterworks. And then the waterworks itself is then gravitates to the quarry reservoir. It's an existing reservoir as part of the South Coast system, so that will be extended. This is a bit of a noisy slide. It doesn't just again supposed to give a little bit of context. You can see on the extreme left, the pale blue would be Umkhomazi Dam. In the middle is good enough scheme. So that shows right on the extreme right would be the close to the freeway. The freeway is just out of sight. So right on the edge, the right-hand edge would be the SAICE cycle plant. For those of you who are familiar with the South Coast, you know there's a massive factory right on the N3 N2 freeway. So the waterworks is be a 1 kilometer rising main from good enough pumping up to the reservoirs, and then a 6 kilometer gravity main to the waterworks. And then Umkhomazi is another 20 k's upstream. So those are the components. So again, for the sake of an overview, we're showing you the number of contracts. There are 5 contracts. There's the two that are finished would be the advanced works, the water treatment works. Sorry, not 5. That's 5 from our side. That's the raw water side that Gibbs responsible for. This shows the whole lot. So there's advanced works for water treatment works, which we had nothing to do with sorting out earthworks platforms. Then there's advanced works, the Umkhomazi abstraction and dam. That was really just access roads and bush clearing. And then construction is currently underway. It's a good enough abstraction and pumping that we're talking about today. This has been underway for the last year and a half, and it's quite the civil works 2 years. So on the way for 2 years. The civil works are pretty advanced, and shortly at the end of the year, beginning of next year, all the mechanical electrical toys start coming in. The Umkhomazi Dam started in January this year. So that's a lot of earthworks been going on there, and that will be a subject of a future presentation, I'm sure. Because the Umkhomazi Dam, just what makes it a bit more different is there's no clay in the area. So Umkhomazi Dam is a rockfill dam with a concrete face to it to make it watertight. And concrete face dams are quite tricky in that if most earthen dams or any fill dam is going to consolidate and settle, the rockfill, the idea is the settlement is small enough that the concrete slab facing doesn't distort enough to crack and leak. So quality controls are very important, and there are a lot of technical aspects with a role. It's called a concrete face rockfill dam. So that'll be an interesting future topic. Then there's tenders received awaiting award and site handover. So the water treatment works has gone out to tender earlier this year, and that's still to be awarded. The Umkhomazi raw abstraction pumping system to the dam. So that's the abstraction that's also ready to go, has been awarded. The good enough rising main, raw water reservoirs and gravity main, which takes water. So the scheme we're talking about today stops at the boundary fence of the high lift pump station, and this next contract will then do the rising main up to the reservoirs and the gravity main to the waterworks. And still to go out to tender is the clear water gravity main extensions to the quarry reservoir. So those are all the contracts that constitute the whole Lower Umkhomazi bulk water scheme. So honing in a bit onto the good enough system. So what you see now is on the top left is the good enough weir and abstraction and pump station, the 1 kilometer rising main, and then you'll see another blotch is the reservoirs. I haven't got a pointer, so I think we would. Okay, if you can see that. And then the 6-kilometer rising main. That will be a challenging project in that although it's only 6 kilometers, the 1200 wide, because you're running down the length of the valley, you've got all the water courses coming in from one side. And although it's 6 kilometers, you've got about 40 air valves and scour valves. So it's like up and down, up and down, up and down. And there are no gentle gradients. It's all steep up or steep down. And the contractor is going to have great fun building that. So now furthering down onto this particular contract that we're doing the site visit for today, the abstraction desilting design considerations. So looking at the abstraction out of the river, the Umkhomazi River is, it's nothing like the Utkela River, but it's still a major river. It's got quite a tight valley, so the valley sides are very steep. So when the flood comes down, the water level, variation of water level is very high. It also has very high sediment loads when it comes down in flood. Again, not as much as the Utkela, but it's very significant. And bearing in mind this is a primary bulk water supply, you've got to supply, Umgeni Utkela have got to supply water 365 days a year. So if you've got a 4 or 5 day massive flood, you've got to still be able to keep on pumping. So there will be, if it really gets exceptional floods and you're pumping mud, you really need to stop and rely on your stored raw water and stored clear water at the quarry reservoir to keep the water supply going to the south coast. And then if necessary, under very heavy sediment conditions, you can throttle back. The waterworks can run at a lower rate, so at least you have some water, even though you're having to cope with huge volumes of sludge. So that's a sort of thinking that needs to have a high level of assurance of supply. Now, so in the design, you want to be able to keep out the sediment, as much as possible sediment. You want to stay in the river. Ideally, you'd be able to suck water out the river, just the water part, and leaving all the dirt behind, but that's not that easy. So the best we can do, we have a design by Professor Gerrit Besson, who was with Stellenbosch University. Most of you will be aware of him. He is the South Africa's expert on abstraction and sediment, dealing with sediment. So the weir is his design, and it's actually very similar to the lower Utkela River. The works at Mandini, the lower Utkela bulk water supply, was done by Oricon, designed by Oricon, which I was part of at that stage, back in 2013, 14, 15. So construction was finished in 2016, a bit earlier than that. That had a very similar abstraction system, and the only difference really is the height, because the Utkela River is much wider, the flood levels are lower, but the structure is very similar, and it's Professor Gerrit Besson's design. We'll go into more detail about still needing hydraulic model testing. Besson's design is designed to keep out as much of the sediment as possible. So you've got all the way from boulders and the flood, where you've got boulders rolled down the river, gravel and sand. The best you can do physically without a major settling tank is down to silt, about 300 micron or 0.3 millimeter. It's like fine sand. You can, by judicious processes, settle out to provide a barrier between the raging river and the pump intake, which will settle out first the boulders, then the gravel, then the sand, and then what you're taking out the river would have only the finest sediment. It's just unfortunate that most of the total suspended solids load. So if you're talking about 10,000 milligrams per liter of suspended solids, at least 75 up to 80% of that is actually too fine to settle out by physical means. And at the river, we limited to physical means. We can't add chemicals because you're not allowed to dispose of the sludge directly back to the river. Now, just in contrast to the lower Utakela scheme at Mandini, there the river bank is quite wide and the waterworks is just on the other side of the river from the extraction works. And the big advantage of that is they've got hydrocyclones to take out the coarser, the stuff that's pumped, but then they've also got primary settling tanks to capture sort of as much of the finer stuff as you can down the silt level, and that can go back into the river in the flood because it's got no chemicals added, and you can just directly flush it back to the river. And chocolatey at that stage anyway. Now here we don't have the waterworks next to the works, so here we've got to pump it and send it by pipeline, and it's got to sit in a raw water reservoir. So you're going to have a problem with. Be careful with sediment settling out in the pipes and in the raw water reservoir. So that's what makes this a bit different to the lower Utakela system. The other aspect which makes it a bit more tricky is because the river valley is very steep, and even a 1 in 5 year flood is a 10-meter water level. The water goes up by 10 meters. And normally, like was done in the Utakela with a wide river, your cofferdam is just pushing earth into the river, a big wide swath of earth on half to block off half the river, and you excavate behind that. And you can do that with a nice wide river. Here it is way too narrow to do that, so you need any cofferdam needs to be a concrete structure. And then, as I say, a 1 in 5 year flood, it's already 10 meters high. So you're getting to the point where it becomes uneconomical. Normally, a cofferdam you'd be aiming at least a 1 in 10 year, 1 in 15 year return period, because it takes about 2 or 3 years, 2 or 3 dry seasons to build your abstraction structure where you need to keep it protected from floods. So if you take a 1 in 5 year return period, over 3 years, you've got almost a 50-50 chance of there being a 1 in 5 year flood over that period. And we have had one flood which came within a meter of that. But so far we've been lucky, touch wood, that it hasn't been a problem for the contractor. The issue, one of the issues, was to do a concrete cofferdam that's only 1 in 5 year, can withstand a 1 in 5 year flood, because if you do make it higher than that, now it becomes extremely expensive. So already that cofferdam arrangement was 80 million just for the cofferdam, all the dealing with the water, the temporary works. So it's a pretty expensive exercise, and if you reduce the risk, that cost goes up exponentially. So you'd rather pay the contractor for having his shuttering and reinforcing washed away than paying for a massive cofferdam. Going on to the desilting, so again, because it's a very tight river, the river banks are very steep. There's no room for the likes of the primary settling tank that needs quite a lot of space, or there are other alternatives. You can have sorry, let me go back. I'm jumping the gun. So the dealing with silt, apart from Professor Basson's abstraction works, the only other thing we could reasonably do is hydrocyclones, and I'll come on to that just now. The site, just looking at the siting of where the weir goes, this site, the photograph you're seeing now, is a dam that SAICE built many years ago on this original farm Good Enough, to store water for their downstream. They don't do it anymore. They had it as a low concrete weir with on the left is a release structure, and they would build it up, but and they would accept that it would get washed away in a major flood, and they have to rebuild the whole earthen dam every time it got washed away. And I think that happened one too many times. So many years ago, they abandoned that, leaving behind just the concrete abstraction structure that you see on the left. And then, so when we looked at the siting of the thing, which, so this is now a view looking at how it was when we started the project. You can see the original SAPI nominal weir. It's only 1.5 meters high, and the diversion structure on the left, which would release it. So that's totally useless to SAPI in that state, because it doesn't store anything significant. That was fine for us. But you can see on the north bank, it's very steep and it's inaccessible. There's no road anywhere near that. So you only have access on the south bank to do all your operations. Again, unlike the Utkela, lower Utkela, that you could get access from both sides. So it did make life easier when you're doing your diversion works, that you could get access from both sides. So that's just another point which sort of made the constructability less easy. It's also, this photograph also illustrates the steep slope. You've got at least a 1 in 4, some places steeper, where you're now going to build all your toys, the pump station, outside the floodplain. Going back to the siting of the weir, it's very important that siting is to make sure that you abstraction works doesn't. Often what happens when a flood, or what does happen in a major flood, as the flood recedes, it dumps its load. So over a matter of hours, as the flood is receding, you get a massive deposit of sediment in the river. And if you're not at a bend where you've got the higher velocities on the outside, and you can have the situation where your abstraction works clogs up, it gets choked up with rapidly depositing sediment, and it's very difficult to flush it out. So the whole purpose of the abstraction works is to create a head difference about 4.5 meters between your normal operating level, where once a flood has gone past and has dropped its load upstream, you can now open floodgates, in this case radial gates, and flush out the entrance to the abstraction works. So where your pump intakes right after a flood are going to be choked up, and you must be able to quickly flush it out. You're not going to flush away all the sediment captured behind the weir. You're only interested in flushing away the sediment that accumulates in front of your pump intakes. And we'll go into a bit more detail there. So the siting, the initial siting of the weir, you want to put it on a bend. So you can see here that you've got a 0.5 kilometer upstream, which is relatively straight, and then it approaches the bend. So you would expect the water to pile up on the outside and help assist scouring away, so it doesn't leave so much sediment as the floods are receding. So this is a 3D model of the structure as designed. Oops, I don't know why it's jumping ahead. So the elements of it, I don't know if you can read the labels there. You've got
Gordon, just use the mouse to show what Duncan's talking to. Gordon can. There we go.
I can't actually see your mouse, is it?
Yeah.
Okay. Yeah, it'll be easy, I think. Yeah. Okay. So you got your weir, which. Oh, okay. Okay. So the weir itself is just to create a head difference. So for flushing, this wall in front here is supposed to deflect your boulders and larger debris that gets washed.
Duncan, sorry, the flow directions from the right of the screen. Okay.
Yeah.
Okay.
From the bottom going through down to the top right. So that'll be a deflecting wall for most of your bigger debris. And then behind that is a slot. And that slot regulates some of the flow into your gravel trap. So your gravel trap will be the middle channel behind there, and the boulder trap is just behind the wall. The gravel trap is the middle section there, and behind that, those four angled channels is the intakes. You'd say a sand trap, which goes to the pump intake. So that right at the back is the low lift pump station. There'll be a drywall arrangement, so you have horizontal split casing pumps in a drywall right at the bottom, with a bell mouth suction inside these four channels. And then those are all flushable. So you have screens at the front for the debris, the finer debris that don't go into your pumps. You have a secondary screen, because when you clean your primary screens, when you lift up the primary screens, clean them, now you're going to have dirt going through to your pumps. So the secondary screens means there's always at least one screen in the way between the pump intake and the intake, the water. And then at the back of the sand traps, there are also sluice gates you can lift to flush the arrangement. Let's see if I can show this angle here, gives you another angle from looking from downstream. So on the extreme right, that part is your boulder trap, and you've got one radial gate. That's about a 3 meter width, 4 meters high. So when you open that out, you get a lot of water flushing through, and it's designed to carry through the heavy debris. And the gravel trap's got 2 partitions and 2 radial gates. So you'd open them together, and we've got a photograph of that for the lower together anyway. Also, just a note in passing, this structure behind that is a fish ladder. So because the weir is too high for fish to be able to jump up, we provided a vertical slot fishway, which allows any migrating fish, juvenile fish, to find their way up a zigzag. It's like 150 slots designed where they can go through one slot at a time, rest, recover their breath in the intermediate like wells, and then go for the next slot. And then they end up in the gravel trap, and they're hopefully smart enough to avoid being sucked into the pumps. But the fish are looking to go upstream, not downstream, so they'll come out at the front entrance. Also, just a point of note or interest, the same was done at the lower Utigela one. And there, the fish ladder, we were always keen to know how it worked, to monitoring it. And the fish experts tell us that when they looked at it, they found that there were some fish that had taken up residence in the fish ladder, and they were using it as a feeding trough to prey on passing fish. So I'm not quite sure if that's a good thing or a bad thing, but we certainly protected from birds, because in previous earlier versions and other schemes, birds would also see the fish ladder as an easy fishing point. The fish eagles and the like would, it's now easy for them to grab the fish. So that's catered for here. We've got a grating covering the fish ladder from external predators, but there's not much we can do about internal ones. In this scheme now, we've got the fish experts are wanting to install sensors, so they're going to tag some fish when it's all finished. They're going to tag certain fish and put in sensors at different points along the fish ladder, and see how it's actually used in the future, and whether some of these guys take up residence or whether they just pass through. Also to note, there's not only fish, you also have crustaceans. This is a video. How do we get the video going? Oops. Okay, so this is a photograph taken by biological guys back in 2013 sometime. This is actually at the Goodenough site. These are Varuna juvenile crabs, and every couple of years you have this mass, what would you call it, migration, where they come by their tens of millions. It's a sort of likened to the Tanzanian great migrations, to the extent that even David Attenborough was wanting to come and do a documentary on this. These are the crabs also need to be accommodated. They can't go really up the fish ladder, but on the other side of the weir, we're creating what we call a creepy crawly ramp, where you have a shallow wetted surface, because they would crawl along the water's edge in shallow water on the rocks. So we're creating a sort of, if they can't get up the fish ladder, they carry on and they end up the other side of the weir, and they'd have shallow water's edge that they can climb up. Well, that's the idea anyway. I'm not, hopefully it'll work, but we'll see. So yeah, the creepy crawly would be on this side, on the near side of the weir. That's not a good representation of it. Effectively, it's just a natural rock surface. So it won't actually look quite like that. We have actually modified it since this model was done. This model, by the way, is done in Revit software, which is excellent for the structural guys, but it doesn't need people who are good at Revit. The idea of Revit is being a 3D model, you've got the accurate representation of the whole structure, and you can generate a long section anywhere in it. Where the old timers like myself and Gordon are used to doing everything in 2D drawings, where you need lots and lots and lots and lots of cross sections. So the idea of you can now generate a cross section wherever the contractor wants it. So if he wants an extra cross section, it's theoretically a click of a button and we can generate it for him. This is a diagram. I hope you can see the detail on the white is what would be taken out in the abstraction works. So that'd be the boulders, cobbles, gravel, sand. The red is the finer part from about 300 micron, or as I say, 0.3 millimeter. And that can go, the part that you can physically settle out or remove by physical means is about 20 microns, 20 thousandths of a millimeter. So even particles that are 20 microns in size, if you put it in a glass of water, it can still settle out in about 15 minutes. So it still readily settles out, and that's we have to deal with in any balancing tank or a reservoir. We are providing means of flushing that out, but we want to. So the weir has taken away the white section. And then we're relying on the hydrocyclones to take out the red section, and the rest has to be taken out at the waterworks with the orangey part. Some of that would settle out and would be flushed from balancing tanks in the raw water reservoir and the pipelines. And the green part has to be chemically treated to coagulate it and flocculate it so you can remove it. And as I say, the waterworks is going to have to deal with massive volumes of sediment if it's going to treat water in the sort of 5,000, 10,000 milligrams per liter sort of level of sediment load. And there they've got it, because it's Craigieburn not next to a river, they're going to have to dehydrate it through centrifuges and cart away the spadable sediment. But you're looking at of the order of 20, 30 truckloads a day if at the higher sediment loads. So it is a massive problem, and thank goodness it's not Gibbs' problem. So you have to ask Ingerop how they're dealing with that. This is just an illustration on the three levels. So you've got the main flow over the weir, the boulder trap, gravel traps, and the purple is the pump channels. So providing the sort of three barriers between your raging flood and your pump intake at the bottom. There's just a bit more detail showing the low lift pump station. So this structure is 20 meters high. That's a 7-story building to take you to a 1 in 100-year flood. So in agreement with the clients, the idea is that you can withstand any flood up to a 100-year return period without it flooding your low lift pump station. If it's more than that, well, you have to dry out your motors and you're going to be down for a while, but there's not much that can be done with that. But generally hydrologists are very conservative. So personally, just a personal opinion that what we designed for is actually a lot higher than a 1 in 100-year flood. But we got about the hydrologists, and that's what they say it is, and that's what we've designed it for. And there's 20 meters high, which you'll see from the photographs Gordon will show you is quite impressive. This is just another show. The red is the mechanical part. So you got the radial gates and the 4 screens. Those will be raised for cleaning when necessary. When you have there's not too much sugarcane fields. The Umkhomazi doesn't have too many sugarcane farms upstream, so it doesn't have anything like the debris load that the lower Utikela has. This is to show you the inside the gravel trap. As I said, it's got two partitions. So the photograph on the left is before the radial gates are open. The radial gates at the far end, and the entrance is at the bottom of the photograph. The other photograph on the right is the other way around, where you're seeing the radial gates are wide open at the bottom of the photograph. On the left is the intake screens to the pump channels, which are at a higher level than the bottom of the gravel trap. And you've got a partition wall to help guide and train the water to entrain any gravel that's settled out in that once the flood recedes. So at the top end, you get the vertical, there's a horizontal slot in the wall, and the water's pouring through there and agitating the settlement, settled gravel, and flushing it out through the radial gates. Now going on to the hydraulic modeling. So this was done at Stellenbosch University back in 2017, 1/40 scale. So the whole river gets surveyed and modeled on a 1/40 scale, and the abstraction structure gets built out of wood, plywood, painted and with the weir, and then they can if it tried out with the different return periods and putting sediment down, which is they use a mixture of sand, and for the bigger particles they use peach pips, which doesn't strike me as quite intuitively correct, but they say it behaves hydraulically very well to model the bigger boulders and the like. So if they find that it's not very effective, the model helps prove that they're flushing. So they put a whole lot of sediment in there and open the radial gates with just a slot which represents a radial gate, and they see that it actually flushes out quickly and effectively, and if not, they change the orientation and try it again. So the purpose of the modeling is it's a very complex process to do it numerically. So the idea is this gives you an exact scale of what will really happen. So if it works on this model, you've got a 99% sure chance that it'll work in practice, and you've got the orientation just right to make sure you've optimized the situation. So at the bottom, that block there is the outlet channel, so you can flush the sand channels behind the pump intakes and flush it back to the river. You don't want sediment piling up there either, so that's why it projects back into the river. That the main flow roaring past would also keep that area, the flushing channel, clear as well. So there are a lot of factors to consider, but Professor Basson got the thing quite well taped by now. There's quite a few of these examples in South Africa. That's just a representation of the flood at a higher level. So we also used the model. While we had the model, we realized this problem with the cofferdam. In order to be able to give the tenderers a good basis to know what to do with their cofferdam, we modeled various things like how much of the river we can block off with a concrete weir, and how much of a gap to leave and what effect that would have. So after playing around with these models, we could then say to the tenderers that if you build a 10-meter high cofferdam and you leave a gap of so much, like we specify the distance from the outside face of the cofferdam to the structure itself. They say that you must build it within 50 meters, leaving a certain minimum gap. Then that constitutes a 1 in 5 year flood. And then in terms of risk events, if it overtops the cofferdam, the insurance will then pay for that, and that'll be a claim event. So it takes the guesswork out of tenderers, so they know exactly what the pricing for, what sort of structure, what height, and what the dimensions are that they must leave free. And so that was like a fixed design specification. So we know how to deal with the floods, and insurers were also on board with that. So they appreciate that so they got a price for the higher risk, that you've got quite a good chance of the cofferdam being overtopped. And you also have to give the contractor a certain period to build it. So the insurers would give you so many months to build the cofferdam, realizing that up until that stage it's vulnerable to a flood coming down. So you really need to start these things in April or so, at the very beginning of the dry season, which does complicate, and certainly did in this case. We were caught short with various delays with this contract, where the contractor wasn't able to get into the river straight away, so it delayed the things. This just emphasizes the depth of it's 20 stories, 7 stories high, as I say. So the low lift pump station is pretty deep. These are photographs from the lower Rutikela low lift pump station, so it's effectively identical. It's just the good enough one is just deeper. The lower Rutikela is 14.5 meters deep. This is 20 meters deep. Otherwise, it's very similar. When this good enough's finished, it look very similar to this.
Same colors and everything.
The same colors and everything, yeah. So just stepping back to take the bigger good enough abstraction, this contract that Stefanuti stocks in JV with Patterson County International are doing comprises the abstraction works at the top end, which we've been talking about, and the low lift pump station is at one building there. Next to it is the standby generator building, so that's built on top of a big mass gravity platform that is upstream. So that is just a mass gravity platform. There's nothing in it. It's all solid, and that gives you a working platform to get access for what was initially intended to construct from that, but also to maintain and bring the pumps in and out of the low lift pump station, and gives you access to the abstraction works up to 1 in 100 year flood. So that's the lower part. The road that bisects the site is actually a public road, a district road. It's a dead-end road. There are only 2 residents living beyond. So on the right-hand side is where you approach from Craigieburn side. When you're coming to site, you'd come down from the right. The road going to the left is only 2 residents who are a bit bemused by all this, because it was such a peaceful valley until the contractor started making a noise and rearranging the landscape.
It's all those fat bras that they're objecting to.
Yeah. So from the low lift pump station, because you're pumping water, water's still got a bit of sediment in it and needs to go through hydrocyclones. That gets pumped. The blue, you'll see in the middle, in this pictures, there'll be a cluster of 9 hydrocyclones in a cluster. One of those is standby, so there'll be 8 operational. So when you're pumping, and the hydrocyclones operate in steps. They operate at a particular pressure and flow. So when you're delivering water from this section, it'll be in 8-step increments, depending on how many cyclones you bring into play.
Duncan, there's a question from Jaco van den Berg. He says that what literature or specs were used to design the crab ladder? I think you've given some reference to it. And secondly, is the generator building built above the flood line? From the model, that area looked flooded.
Well, the generator is built on the 1 in 100 year level. Okay. The Verona Clab creepy crawly ramp is not, it's anecdotal. It's what we were told by the fish specialists. You need that they basically crawl along the wetted edge, the edge of the river, just inside the water, because they need to be kept wet, but not right in. They can still short distance there if the water current is not too strong.
Thank you, Duncan.
On the weir, we've got a low section right up against the abstraction works, and then the rest of the weir is 300 millimeters higher. Now the creepy crawly ramp goes along the front of the weir to the far side, just around that corner. The section is also the same the same level as the low portion, so you have water going through both sides. So it all has that wetted edge along there.
So if you look at the screen here, so that section, the low lift section for high accuracy of gauging the river flow, because how it works, you've got Sappi Cycle downstream who draw about 1.7 cumex and then you've got the environmental reserve of 1 cubic. So there must be at least 2.7 cubics passing by at all times. The fish ladder at low flow would be about 100 liters a second, so relatively negligible. So the low notch width, 15 meters, is designed for gauging, and then you have another 300 step. But the creepy crawly on the other side is at the same level as the low lift, so there'll always be water flowing. They won't be going upstream in strong flows. They'll only be very low flows. I think it's this time of year, spring, beginning of the start of the rains, that they migrate.
And is that built already when we look at the
No,
progress?
not yet. We haven't done the contractor's been concentrating on extraction works itself first, and then he's still got to get to the other side. That will happen in 2 years' time. So getting back to the, so we ended up pumping up through the hydrocyclones. That would need to go into balancing tanks. So you'll see 2 compartments there. The idea being that because the hydrocyclone we'll show you just now how that works. The part that gets pumped away is go into the balancing tank, but because it's still containing sub 25 micron particles, there will be some sediment. So in order to flush it without taking the system offline, we have 2 tanks. So you take the 1 tank out of commission, drain it, and then use the other tank, pass through flushing water, and you flush out the sediment when you need to on the one side of the balancing tank, while maintaining the flow to the high lift pump station and on to Craigieburn. That's why it's got 2 compartments, and it's designed for flushing. Just another modeled view of the elevation. That's this you'll see from the photographs actually looks more dramatic than that. This looks relatively tame, but the photographs will do it justice, I think, and how steep it is. We've got this massive retaining wall on the front, which we'll talk about with the photographs. Getting back to the hydrocyclone, so as I say, we want to take out as much as we can physically from the abstraction system. In looking at the reviewing, although the feasibility and preliminary design was done by AECOM, we did have another relook just to make sure that we haven't missed something. So we did consider, like, what are the options, because this is an important step, and because you can't, it's got to be pumped some distance, it's important to do the best you can. The hydrocyclone is very compact, as you would have seen from the previous picture. The one alternative we thought of, given the steep site, would be you get GRP pipes, like 1.8 meter diameter, and you have a lot of them, 20 of them all in a line. You've got the steep hill, 1 and 4 slope. One possibility was to have like a pipe organ where the water's flowing up, creating very laminar conditions, flowing up these pipes, and you then flush them one by one, alternating while pumping continuously. And at the top, you then have another transfer pump station to send it up to the reservoir. The one advantage of that would be you do away with the hydrocyclones. That had some issues at the lower Tigela one. So we were just wondering what other alternatives there were, but it was decided this is too new to try on a major bulk water scheme. So the client wasn't keen to do something new. They said if it was a small waterworks, they would have gone for it, but being a major bulk primary supply, they were keen on sticking with tried and tested. The usual one that's done is long settling channels, but these are very expensive and take up a lot of room. They'll be about 150 meters long and designed to create laminar conditions flowing down a channel, and then you take out one channel at a time and flush out the sediment back to the river. So that's just by way of illustrating why we said it. Really, there's no other choice but hydrocyclones to take out as much as you can. And although you're only taking out a small percentage, maybe at most 5% of the sediment, it's still worth it, because that's 5% less which gets taken out of your balancing tank and your raw water tank, because you're talking about hundreds of tons a day of sediment altogether, which goes to the waterworks. But if you can save 10 tons of that a day, not settling out in your balancing tank and your reservoir, you save a lot of maintenance work. So the idea is to use the hydrocyclones to take out as much as possible. Now, the nature of hydrocyclones is they're designed for the mining industry to separate crushed ore, slurry from the water. So you want to separate out your crushed rock with your gold or whatever in it you're trying to extract. And that's normally done as quite a thick slurry. Here we're only talking about up to 1% suspended solids. So it's much less solids than would normally be used in a mining application, but the physical process is the same. The water comes in tangentially at the top, and so it comes in at a very high velocity and spin. You have what's called a vortex finder in the top middle, and at the bottom you've got your underflow spigot. So the size of the vortex finder, the size of the spigot, the geometry of the hydrocyclone determines how efficient it is in spinning. The heavier stuff gets thrown to the side and ends out at the bottom. So of 100% inflow water, you'd have about 5 to 8% coming out of at the bottom, which goes back to the river as taking your heavier sediment with it. And the 95% is your overflow, which now can go to your balancing tank. The higher the pressure, the higher the spin, the finer the particles you can separate out. But economically, we did our sums and looked at, we worked out that about 14 meters pumping head, extra head. So this is absorbing 14 meters of pumping head to spin it. That's quite a lot of energy when you're talking about 1.5 cubics of flow to feed your waterworks. If you bumped it up to 20, 25 meters, you could extract a little bit of extra sediment, but that extra energy is not, there's a law of diminishing returns if a higher pressure. So we settled on 25 microns and 14 meters head pressure as the optimum.
Duncan, before you step off that, there's a question and observation from Alan Chamali. He says that on the hydrocyclones, even though rugged with respect to the elements and corrosion and weathering, etc., is it preferable to have them under shelter and or in a building? He's aware they do have other components which are more susceptible compared to the cast iron bodies of the hydrocyclone themselves.
The hydrocyclone, you can see the picture on the right. That photograph is the lower Umkhomazi, lower Utikela hydrocyclones at Mandini. They're pretty rugged. It's just a steel body with the water spinning in it, and it is rubber lined for abrasion on the inside. And bearing in mind, this is designed for mining slurries, which is far more abrasive. Crushed rock is a lot more abrasive than river sediment. So we're not concerned from abrasion or corrosion. That the rubber lining on the inside can be replaced if necessary, but it's unlikely to be
and the outside is all galvanized.
No, it's mild steel painted.
Okay.
But the paint, you can have a good quality coating, epoxy coating on it, and because it's out in the open, dries quickly. The rust is not a big issue when it's not actually submerged.
Okay, but I mean, this is quite close to the coastline,
Yes.
so you're not worried that being in much closer proximity to the coastline, the probability of rust is higher than we're at 50 k's inland.
Not really, because the ones at lower Tigela are also close to the coast. And they've been there for 10 years now, more than 10 years, and they're not showing any signs of
so how long after the, let's call it, full operational stage would it need to be maintained? Because maintenance, most authorities can't spell. So
it depends hugely on how the river, what the sediment, what sort of floods you get coming down the river, because most of the low flow season, most of winter, the river quality, you'll see from the photographs Gordon will show, this time of year the river is actually very clean, and there's totally no point in putting it through a hydrocyclone. So it has a bypass on it that you don't have to waste that 14 meters pumping head. So then it'll sit idle only when it gets up to chocolatey. So the next slide we show is a pilot plant. because it's a bit of an unknown quantity, and we also need to be able to tell Umngani Utikela when you need to bring in the hydrocyclone and waste that extra energy. When is it cost effective to bring in your hydrocyclones and pump that extra energy 14 meters head? And when is it you're wasting your time? You're going to remove such a little bit of silt that it's not worth that extra energy. To answer that, we've part of the contractor's job is to run this whole lot of tests on a pilot plant. So the yellow thing in the background is one of the hydrocyclones. It's one of the actual hydrocyclones.
So it's a tiny one, is it?
Actual size.
A tiny version of the big thing that you...
No. It's a full size one.
Okay.
I haven't got alternative view. It's not that. It's about 2.5 meters high, more than that, 3 meters high. So it's not that small, but compared to other toys, the pumps and the concrete structures, it's very economical footprint. So we're still battling, the contractors battling with the dynamics of putting through the sediment and getting meaningful readings that actually make sense. The couple of the learning curves to go through, and we're still going through that with how to make sure we get a representative sample coming through, because it doesn't settle out in the main tank. This is just a further detail. So the blue, the hydrocyclones, the lower pipe would be when you bypass it. So when we deem the water not worth putting through the hydrocyclones, you'd open a valve and send it straight into the balancing tank. This is a model of the high lift pump station. It's got 5 main pumps, about just under 1 megawatt each, 6.6 thousand volts motors, make them more compact. So on the left is the pump hall. These major orange boxes would be the variable speed drives. These are very pricey animals, about 5 million rand a pop, and very large and very heavy. So the electrical hall is quite a major part. The reason why we need variable speed drives is because the power coming from Craigieburn, Eskom's power, it's on a spur line, which you don't have the benefit of a ring feed. If one side goes down, you can go on another. So it's a dedicated 22 kV power line, about 7 kilometers away, and they aren't able to handle the massive starting loads that you'd get with conventional soft starters or other means. So they insisted, Eskom insisted that we go variable speed drive to keep the startup loads very low, and also it means you can fine tune your flows through your hydrocyclones to get the exact flows that you want.
And are those, and that Eskom feed, is it outside of the switch on, switch off for load shedding?
No, there will be
no guaranteed power.
Will be subject to load shedding, but don't forget we've got 12 hours raw water storage. So if there's load shedding, unless it's more than 12 hours, you won't have a problem. And then there's also 24 hours clear water storage at the Quarry Reservoir. So there is quite a bit of buffer for the short. And running these, we've got 4 2,000 kVA generators, standby generators, which is not even running the whole thing. The whole thing's 5.8 megawatts capacity. The low lift and high lift pumps will absorb 5.8 megawatts at full output. The generators will run 3 of those comfortably, but you don't want to pay the diesel bill. That's going to be well over 1,000 liters an hour consumption. So you only run them if you really have to. But when you need to run them, because it's a primary bulk water supply, you just got to pay. K and Batal. So low lift's got 4 pumps, the high lift's got 5 pumps, so they're obviously slightly smaller individual capacity. Standby generators, we covered that. Pipelines, general works, so these are 1,200, there's a 1 meter diameter pipe, low lift going to the things so it's higher velocities to keep the velocities up, to go through the hydrocyclones and not have too much settle out in the pipes. And we've got 1,200 pipes going up to the reservoir and 1,200 pipes going to the waterworks.
There's another question from Umkhomazi. Was it the designer's choice to choose VFDs instead of capacitor banks? I don't even know what that means, but hopefully you do.
Capacitor banks more for correcting power factor, that you don't have too much of inductive load, which gives you artificial pushes up your electricity bill without benefit of extra power. So capacitors would be used to bring it back to a power factor, now the lagging or leading back to 1. But variable speed drives do that as well. So that's a side benefit of the variable speed drives. Capacitors also are like Chinese electric cars; they're liable to explode. They can be dramatic and then need to be replaced quite often. So that's my side. Any other questions on that?
I've asked all those that have popped up in the chat. Is there anybody that wants to ask a question of Duncan before we hand over to Gordon and start looking at more of the actual site itself? Your mics have been enabled. If you'd like to just pop up a hand, we'll acknowledge you and you can engage directly with Duncan. Duncan, I have enabled Dee as a co-presenter, so you did say any difficult questions you'd give to her. We're going to leave the meeting now. It looks like we're fine, so let's get going with.
Sorry, Tom, there is a question.
Yeah, no.
Alan.
Go ahead, Alan.
Hello, Duncan. It is decades since we last spoke, but anyway, here's a question.
Hi, Alan.
On the hydrocyclones, I see they being more regularly used on different projects around the country. What interested me mostly was that you could use let's say, a more miniature hydrocyclone or a model to get everything working. I see you battling a bit, but it would seem to be the trend. How is the price of that model testing with a semi-prototype hydrocyclone fitted into the project? Or does that come into Gerrit Besson's fee?
No, it's a valid question. But because Umkhomazi Utkela only got the lower Utkela so far, and no tests were done on that, so they're not quite sure how it performs, and they're not too fussed there because they've got primary settling tanks, so whatever they don't catch, even if they don't work at all, the primary settling tanks will catch the sediment, which can go back to the river. Here it's more critical that you don't want to have it settling out in your pipes and tanks. So the model, I'm trying to remember what it was, about 1.5 million, just under 2 million. The scheme itself, this project is a billion rand. So in context, it's not much, but it will give Umkhomazi Utkela valuable insight for future schemes. It gives them more ideas to give them much more, give them a hard experience for when the next big bulk water scheme is designed as to like how well hydrocyclones work. This is the full size hydrocyclone. It's not a model like the hydraulic testing done at Stellenbosch University is 1 in 40 scale. This is one of the hydrocyclones, and when this project is the pilot plant's finished, it'll be dismantled, and that one hydrocyclone will join the 8 others to form the permanent works. So the hydrocyclone is the permanent works.
Thanks very much for putting it into perspective. Thanks, Tom. Thanks, Duncan.
You're welcome. Anybody else? We won't let Duncan escape.
Any more hands.
Okay, cool. Thanks, Ollie. Right, Gordon, over to you. You want to?
Okay, thanks. Edwin, I'll give you what you can, yeah?
Just can you confirm you can hear Gordon? He's whispering in the room. He's got to project his father
Protect my voice.
punishment voice. Yeah. Ollie, we good?
All good to go?
Yeah, thanks.
We are
Duncan.
good, and it would appear that we're getting a lot of thumbs up, so I think we're good to go.
Excellent.
Okay.
Over to you, Gordon.
Okay, so what I'll do in this little presentation is give some overall headlines about the project itself. And then we take daily drone photographs, and we've got a circuit that the drone flies on. So I've taken images from certain aspects and I've put those into a video. We don't know how it's going to work while we're doing it, but yeah, we'll talk to it and we'll stop when we need to and explain certain things. And then we've also got some videos that Esmond has taken for us, and we've collated those into a whole lot of sequences which we've collated into videos. And again, we'll go through those. It's going to be a repeat of what the photographs are, so it might make sense to talk to the photographs and then watch the videos, but not necessarily talking unless there are questions. And then we can see if there are questions at the end. That's our project signboard. It's been up quite a while, but it's still got Umgaining water and not Umgaining Tukela water. The project is also co-funded by...
Is that a non-compliance issue on site now?
I thought about whether I should leave it there or not. It's co-funded by Department of Water and Sanitation, so we've got them on the board as well. The employer, as we said before, is Umgaining Tukela water. Contractor is Stephanie Stocks. Spelling mistake there, I can see PCI Consortium. The contract sum was 916 million, which included VAT, and the commencement date was the 6th of May 2022, and we started on site on the 1st of June. It was handed over to the contractor. The contract duration 40 months. The original end date was the 6th of September, and we have had various delays for quite a number of reasons, and the current completion date is the 10th of April 2026. We have had an increase to the contract sum through additional works that the employers asked us to do, so we're now up to 955 million, and I guess by the end of the project it will be over R1 billion. Expenditure to date, we're just over 500 million, including VAT. Progress, the contractor is on program, pleased to announce. Progress, we're 57% complete, and that expenditure about 50%. And the reason why it's lagging the progress is that the high expenditure items, which are the hydromechanical equipment, will start being installed from November going forwards, and that's where a lot of the high costs are.
Gordon, while you're talking about the specs of the contract, a question that's popped up is what contract document was used? Is it done on FIDIC or NEC?
No, GCC 2015.
Okay.
Because it was civil, mechanical, electrical, again, you decided to go with the GCC.
No argument from me. SAICE document makes a lot of sense. And Gordon's on the committee, contractual affairs subcommittee, so you should know the document.
The contractor is obliged to use contract participation goal partners, and their target is 35%, so it's like 212 million, and to date we are up to 70 million. Headline quantities: bulk earthworks which are payable is about 40,000 cubes for the extraction work site. There was an advanced works contract which didn't go ahead, so it was added to this contract as a VO, and that was for the bulk earthworks for the raw water reservoir site, and there the contractors removed 54,000 cubes. We didn't have to take it too far away because we put it in the valley next door to create a platform for the contractor for that project. Mechanically stabilized Gabion walls, we put about 1,300 cubic meters in. Concrete, both concrete for the permanent works and for the contractor's temporary works. Structural and mass concrete are about 10,000 each. So we've got about 21,000 there, and at 5 cubes truck, it's 4,200 loads. So I guess the truck drivers are getting used to the road and they can drive up and down there in their sleep. So far, 1,400 tons of reinforcing have gone in, Okay, those other figures I've mentioned already. You've seen that picture because Duncan has shown it already. He stole it out of my presentation. Esmond took that picture about 2 months ago, so it's, if you get the lighting correct, you can get quite a good view of the early morning valley wintertime. And that one as well. It's a view from the high lift pump station platform down onto the abstraction works. Colourful sky in the background. The river can get quite angry with you too. That was early 2023. Okay, let's see how these drone images work now. So that is right at the beginning of the contract. You can see the diversion structure over there. The water is very clean. This is the middle of winter. This is the low wheel wall, which is the upstream toe of the earth embankment that SAPI had. To start proceedings going, the contractor needed to get across to demolish the weir from this side going backwards. But there is a diversion through that structure there. So we put in temporary culverts on that side and then created a platform over that to get to this point, and then we diverted the flow. That's the platform for the low-lift pump station site. The lower site camp went in there. The main site camp went in over there. It's in the early days, still establishing, but getting going with the work. That's the contractor having got across and about to demolish the weir on this side. And I think that they probably have demolished the concrete over there, and they just need to remove the earth embankment. What is that for?
Probably just to help all the section.
Yeah. All right, then the next one is having broken back to there, access moving around all the time. Sorry, I mentioned that we've paid for about 40,000 cubes of material to be moved. You've probably moved double that in doing your temporary works. Because access is a problem, creating accesses and what have you have taken quite a lot of effort. And it's actually been fascinating to see how it's been done. Right. Then the whole weir has been demolished, and the cofferdam wall around the outside was being created. The earth embankment cofferdam wall, so that the permanent cofferdam wall could be constructed. At this stage, the contractor was concentrating on doing the abstraction works, which sits here, and that's the position of the low-lift pump station there. There you can see they're setting out the foundation of the cofferdam wall. They've already started excavating into the rock here for the abstraction works, and the excavation for that is quite complicated in that we've got different levels for some of the elements. Having said that, we were quite fortunate in that the rock levels were higher than, or the competent rock levels were higher than we anticipated. Because what we thought we might need to do is actually go down to competent rock and then do engineered backfill underneath it, but we didn't have to do that. The rock there is
so that's a saving to the project.
It's kind of cost us a bit of time.
Yeah.
And also that we couldn't do, I'll come to it later, we couldn't do bulk excavation. We had to do restricted excavation because of what happened. I'll get to that shortly. But it's pretty hard rock, and we had peckers in there going for months, to be quite honest. Okay, at this stage, that's just more a native photograph I have to get to just more same. They started at this point. They've started doing the basis for the cofferdam on this side, and on, well, this is the eastern side and the western side. They left the middle section out because they needed to first cast the first section of the weir block and the first section of the apron slab, because the cofferdam wall had to go over that, so that in the future, when we take the cofferdam wall out, they can work in the dry to get to the far side of the river. That diversion structure in the back there, only part of it falls into the new works. So we needed to trim off the downstream section of those two walls there, and the rest of it was going to be built into the mass gravity platform. But the position of that was highly appropriate for the contractor's tower crane to go. So we filled what remained of that, we filled with mass concrete, which created a perfect foundation for the tower crane. Just a little bit further with that same section of work.
And from a timing perspective, in terms of your start of the project, where are we in the time frame of the project now, Gordon?
Okay, we started working on the 1st of June. This must have been, well, this was after August. And the reason I'm saying that is you can see that there's vegetation that's growing in there. And at this stage, we'd probably just come back to work on the site because of socio-political issues, and there were quite a number of issues at the start of the contract. We had 2 delays of about 10 or 12 days, and then things started getting a bit tense, and between the contractor and the employer, they realized that something needed to happen to sort this problem out. And it was agreed that they would suspend the works. It was going to be an amicable suspension, but that clause doesn't exist in the GCC. So the employer...
Trust you've put it in GCC 2024.
We suggested to the employer that they suspend the works, because it then flows according to, I think it's clause 511, whatever, 511.3. And the contractor came to the party and they said that that's fine. They would then only claim for costs, not for P's and G's at daily rates, whatever it was. And, you know, everybody came to the party on that. So
it was ultimately an amicable.
It was, but it had to be done through
via the available clauses.
Yeah. At that stage, nobody knew how long the stoppage, the suspension was going to take place. And not the only factor, but one of the factors was that the contractor at that stage had just taken on 50 labor. So if you have a socio-political problem, you've just taken on 50 labor, you really don't want to get rid of them either. So
you create a bigger problem.
Yeah, and we just didn't want to go down that road. Anyway, it got sorted out. It took about 2 months. And I said earlier on that the contractor was concentrating on the abstraction works, which is on this side of that diversion structure. Because of the initial delays and the suspension delay, they weren't going to get this wall up. It had to be up by, I think, the 31st of November. That wasn't going to happen. So we had 2 options. One was to abandon the works in the river till the next dry season. That could have been a 9-month delay. Alternative, what the contractor came up with was an option to build another cofferdam wall there and to concentrate on the low lift pump station, and then leave this to the next dry season. That needed extra works. The projection was with the P's and G's that, because they had to resequence their program. The that would have then taken it up by 9 or 10 months. If they resequenced the works and did the low lift pump station and got back into the extraction works in this dry season, 2023 dry season, which they did, we could then pull that delay back. And we thought we were actually going to get a saving, but typically we probably broke even on that. But I think it's a win-win situation anyway. I think at that stage we've now cut off the walls of the diversion channel there, and they've started with the excavation works on the pump station in the background there. And there, that's the earth embankment, and you can see they've started casting, breaking up rock there, and they've started casting the wall of the low lift cofferdam over there. Now that wall was also for a 1 in 5 year flood, but because it's, you've got a much wider river section that could be lower than what this wall needed to be, and that needed to be done by the 16th of December 2022. And I think we finished it on the 17th of December. And we were fortunate that we did, because that's when the heavy rains started coming.
So that view you see now is that first sort of embankment for the cofferdam, the outside, has been washed away.
Yeah.
The contractor
Flooded, not washed away.
Flooded.
The contractor recovered some of it because he needs that material
Yeah.
for his access.
Yeah.
But yeah, eventually they lost.
And then you've got to go and find your footings and things that you started working with under slush and stuff. Because there was some concrete cast, the footings for that cofferdam.
No, they're there.
Oh, they're there.
It's that wall there.
Okay.
So that's debris from the floods that's brought onto the reinforcing. And it's, I think they were white 20s or white 25s, and every one of them got bent over. So the force of the water is quite high. Yeah, so I think at that stage the water level got to almost the top of that the low lift cofferdam, and it did get a little bit flooded, but when they dewatered that regularly all the time. Then you can see the reinforcing and the walls of the low lift pump station going in. How can you remember the size of that?
It's 1.4 meters thick at the bottom.
No, I know this, but size wise?
Oh, the length times the width.
35. Is it long as it? Anyway, 460 cubic meters in the floor. Now, that's the biggest pour we've done today. We started at 6 o'clock in the morning. We finished at 2 o'clock the next morning.
And batched it on site, because you said access with ready mixers.
No, it was all ready mixed.
I brought trucked in.
Yeah.
Scottsboro.
The contractor was going to put up a batching plant over there, and the site camp is going to be on a platform right at the top of the site. The views would have been spectacular, but access up and down would have been quite tiring.
And we're hoping for that.
You would have looked a lot slimmer than he does now.
Anyway, so when that floor was cast, obviously you needed to cure it, and the easiest way to do it was just flood it with water. We did that for several days and got in and carried on with what we needed to do. So this is several months later, because you can see the water now is quite clear and it's starting to drop. So I think we'll have to get in shift more. Okay, maybe not the middle of winter. But anyway, there. Okay, at this stage, the contractors now re-established this earth embankment and can get going with the weir and the entrance slab in that section there. The walls are starting to come up. That's the first weir block that's going to be cast. That's the shuttering that's going up. There, they're pumping the first section of the weir. Now that's 6 meters wide, Originally, we thought it was going to be 6 meters deep, but because we could bring the foundation levels up, it's 4.5 meters deep. And Wits University, Professor Bannum did heat of hydration projection studies for projection models for us. And ideally, it was to cast 1.5 meter lifts 4 days apart. They checked that we could go up to 2 meters, but going from 4 days to 7 days didn't make any difference either. So it suited us with 4.5 meters to go 1.5 meter lifts and the
what MPA concrete
it's
is
25 MPa.
25 MPa.
Yeah.
The entire, all the structures or just the weir?
No, the weir. The most of the structural concrete is 35. 35.
Yeah.
But the waterproof or the water retaining concrete is all 35 MPa.
All has a very high pulverized fuel ash content.
Yeah. And that's the last section cast with Hessian over it. And then you can see the getting going with the cofferdam walls here, the walls in the background. Now that once that got to a certain level, we could then start demolishing the low lift dam around it, because this was also in the dry season, so we're happy to use this as a protection. Constant problem was having peckers in the bottom there. But a hell of a racket. It's not quite nowadays. Casting the section of the floor to the abstraction works.
Is that far right, which would be west, eh? The west, the coffer there, is that into rock in the bank, or how is that keyed in?
It's anchor grouted into the
To the bottom
of the rock.
Okay.
Yeah, because there's the rock level from this rock level, it climbs quite quickly out of this out of the valley here. You can see the fishway starting to take shape there. As you see, as these photographs go, you'll actually see the different elements that Duncan has spoken about taking shape. And then that structure there is 20 meters high to the 1 in 100 year flood. I think we'll just run through these. I don't know if there's anything more that we need to talk about, otherwise just show people. And these photographs are all about a week apart. I've just been selected random ones, and yeah.
Now you're heading into a rainy season again, are you?
Yeah. It's December last year. The contractor has put in a culvert over here, and they've only just recently put in one at the top end over here. Now that is to create access. We've got to divert the flow through the structure once the hydromechanical equipment is in there. So we can go and demolish this cofferdam wall and then carry on building across here. So we have to get access into here to build the earth embankments on the other side of where the weir is going to be built. So that's what this is for.
And what happens to those when the project's finished?
Fortunately, it's a high quality concrete wall that's just going to go.
No, the cofferdam, I'm talking the culverts.
Will
Also, so it's in theory
so
expensive temporary works.
Yeah.
That's in the way of the flushing system.
Yeah.
Because the hydraulic study said that there were rocks in the river down here which had to be taken out as well to take it down to the lowest level of the fishway. That's the starting of the flushing channel there, the downstream end of the flushing channel. Those are the sand traps going in there. Those will be the gravel traps and the boulder trap going in there. contractor stopped the high lift pump station walls at a certain point below the final level. And the reason is that there's a cantilever gallery on the end here, which needed to be supported off the top of those. Don't support a cantilever, it supports itself. Anyway, it's on the top of the sand trap channels on that side. So the sequencing changes caused by those delays has had quite an impact on what is happening. It's quite an imposing structure when you stand in there. You see that's probably I'm trying to see. These are all taken at lunchtime every day, so you don't really see people. But man feels quite insignificant in the bottom here. Okay. At the back of that structure there, you can see the top of a retaining wall. Now that retaining wall is on the top of a mass gravity wall, which was going to be roller compacted concrete. But because of issues that we've had and access being a problem to this area that needs to be filled in, the contractor needs access to here. So we haven't been able to do that platform.
So that's the left and right of the tower crane. That's that concrete deck that you saw in Duncan's rendering.
So that wall there is a little 1.2 meter high parapet on the top of that retaining wall. We have the same going up on this side over here. And that wall needs to be filled in to the underside of the generator.
That was initially conceived as a roller compacted concrete on the outside, so you did like roadworks, you do layer by layer, with the middle bit being cement stabilized sand, and then the idea being you could have done the platform first and then put your tower crane on top of it. You now got a nice working platform to do all your RC work, but with the sequencing and the delays that went out the window, and so now it's gone to mass concrete. The middle will still be filled with cement stabilized sand.
So the wall going around here, like I say, will be the same height as that. So that's sort of quite a way to go on that side. In fact, you started with 3 or 4 panels over that wall. Because of the heightened access here, on the inside of those sand traps, you've also got cross walls. We've got sluice gates and screens. So it's, you've got this massive structure, 20 meters high, and it's got to work inside there. It's quite difficult. And getting back there to do remedial works is going to be awkward. So the contractor's been very diligent in actually, once they've cast it, they do the remedial works immediately. And then once you strip the shutter or the scaffolding away, you've got good looking concrete. Okay. So now I've got, that's very similar from a different aspect. And I've got these ones of the high lift pump station and the balancing tank. So you can see access has always been a problem. Very steep land. All of those structures are founded onto competent rock. Either directly onto rock or onto mass concrete foundations which go down onto rock. The problem that we had is that at that end of the platform, the rock formation fell away quite steeply. It was the transition from incompetent rock to good rock was a bit higher than what we expected. So in that corner, we tend to have quite deep mass concrete footings under our strip footings. The infill under the surface bed in the pump station is all cement stabilized sand. The pump plinths all go down onto competent rock, and then they're supported by the cement stabilized sand as well. So they're way bigger than the mass that you need for dynamic loading. But like I said, this platform up at this end over here was going to be a side camp. Like I said, wonderful views, but it's kind of trekking to get there. Kind of in the background, you can see what was going on at the same time. That there's an isolation chamber. It's an isolation valve for the rising main. You can scour the rising main from there. The air valves in there. So in itself, it's about 7 meters long, by about 4 meters wide.
And
about 5 meters deep.
what's happening in with the other tower crane? What is that structure going in there?
Sorry, at this end here is the balancing tank. So that's the floor of the balancing tank with the outside walls. They haven't started the buttress walls in the middle. And then that's the high lift pump station in the background. So at this point, we are really only doing the foundations of the high lift pump station and the floor of the balancing tank.
And that's at a level outside the 1 in 100 year.
Yes.
This is probably 30 meters above.
Okay.
That there.
It'll have to be a biblical proportions flood to reach that, in which case people won't be around to
Some of us lived through Des Moines. That was almost biblical proportions.
So the contractor was able to use this as a laydown area. You know, the site offices for this section originally were here, but because of access problems to put the raw water rising main and the HDP scour for this end, eventually we had to move these up to the platform top. You can see the frame structure starting to go up. It's not a complicated structure, but we've got a series of different levels and it's not continuous floors across, so it was interesting. And the contractor wants to be out of this upper section by November this year. When I say out of there, the civil works contractor to hand over to the mechanical department to go and put in or start installing the pumps and the gantry cranes and the electrical equipment and whatever. I'm just going to jump ahead, really at 26. Those are the eaves beams, and after that really it's stub columns and another central column going there which should support the steel rafters for the roof sheeting. This is we keep on hopping on about how steep it is, but the access road up to the site will come up around here, all the way around that building for any heavy vehicles to come in.
Just because of grade. You can't go straight.
Yeah.
So that road's at 15%, which you don't really want to go much steeper than that.
So even the district road is going to be raised by about 3 meters.
Yes, the district road from about there to about there is going to be raised, particularly at this end of it. Because it needs to come up to that level there. So we have mechanically stabilized guardians around here. We have another section along the bottom there, which we have to raise. And I'll show you on the video clip that we've got, the highest point of that mechanically stabilized wall is about 15 meters high. So if you stand and look up at it like this here, the walls of Jericho, I suppose. All right. That's not where I want to do that. It's just, I'm not going to show you all of the video clips. I'm going to go to the one that we did yesterday. This is about 10 minutes long. I think we can just play it through. There's the questions. We'll take us through to 6 o'clock. Yeah, that's the.
So that's effectively the state of the site
yes,
as of now.
Yesterday. Yes. Yeah. Well, no, it's not. No, there's a clip. I've got clips of the ones yesterday. This was taken a couple of weeks ago. The reason I'm saying that is that all the brickwork on this structure is now complete. So, yeah, that's.
Now we can see people relative to the structure in terms of size.
Yeah.
Here's your mechanically stabilized gabion. So, sure.
And what you've got on that, each gabion has got a tail mat,
Reinforcing mat, yeah.
a reinforcing mat, and then there's a propylene reinforcing mat that goes back 4 or 5 meters. So at every meter you've got that, and then we
It's really anchored into the
backfilled over that cement stabilized material. So that whole block is actually a gravity structure, not just the gabion. The gabion is really the face into the mass structure.
If you plant, ivy or some at the top, it will become the hanging gardens of Babylon.
There you go.
Yes, this is yesterday.
There you can see the brick infill's done.
Brick infill and the wind block panels. No, I don't say wind block. The double pane panels at the top there. The contractor had a problem getting what we'd specified, so he thought he'd create his own precast block. And we stuck it in with silicon. We thought, well, let's test one to see how it works. And he got 2 sucker things and picked this block up. And the block weighs about 75 kilograms. And the 4mm glass didn't shatter. So we said, well, that's good enough for us. Yeah.
So it's a precast concrete with a glass pane within it. So you've created your own glass blocks.
Yeah.
Or they have.
Yeah.
Okay.
And then these will be vents for louvers to go in. We've got roof sheeting which goes up. And the central, I think the columns on the eaves beam at the top, they're about 2.5 meters high. They're not a full story.
The variable speed drives pump out 150 kilowatts of heat at full tap. So it needs lots of ventilating, and the idea is you pull the air into the VSD cabinets and duct it directly outside rather than into the room, the VSD room. Otherwise you need a hurricane to keep it cool.
It just gives you an indication there how steep this.
So just Gordon, for a putt marker like me, I like the part about the road. The rest means nothing to me. The water gets extracted from where you've got fish ladders and all those fancy gadgets Duncan spoke about. Then it's got to get to these things up top. Is that the pipeline you spoke about? You mentioned a 217-meter pipeline as part of this phase of the project.
Correct. It goes through that mass gravity structure around where the generator room will be.
Yeah.
And then come across the road.
Under that district road.
Under the district road.
Yeah.
And the rising main, so 1 meter diameter, has been laid from there up through.
Is it in the ground already, or will it be built?
No, it's in the ground.
It's in the ground already.
Yeah.
Okay.
And I'll say it again, access is a problem.
Yeah.
So we have to lay that, then backfill that, and then go and create another trench and lay the HDPE pipe.
Right.
The scour pipe to drain the balancing tank back to the river.
Those are the pipes there.
Those are the steel pipes, the HDPE pipes lying down over that. Those are waiting, and those will go in down back to that point over there.
And the hydrocyclones in the foreground, that front box by the balancing tank.
And then that capacity, that storage Duncan spoke about for a 24-hour, where is that in the picture?
But the 24 hours will be right at the end of Quarry Reservoir.
Okay.
But the raw water storage, 12-hour storage is 1 kilometer up the hill.
Okay.
So you've got pump up to the raw water reservoirs, which are open-topped reservoirs with scour flushing facilities that you can flush it. And again, we have a 400 diameter HDP pipe that would come all the way back down the kilometer, back down to the river, or super tube we call it, because it would be supercritical flow.
You can see the pump prints inside there. It's the isolation chamber. Just trying to get the perspective on how high that wall actually is.
So there's your contractor made glass bricks, that what we could see in the photo.
So the brickwork on the outside is dark brickwork. The brickwork on the inside is a pale face brick, obviously to make it lighter. Okay, now this whole area here is what needs to be
backfilled or stabilized
to that level there.
So how
that's
many
material.
cubes is that going to take? And where do you get that material from?
There's no shortage of sand in the area. There's big sand winning operations nearby.
In the riverbed?
No, well, downstream there's sand winning operations.
But from the river?
Yes, some of it be from the river, some of it be from borrow pits, the decomposed.
There's also a quarry at the top of the valley. We get material from there too, from the cement stabilized.
So decomposed gneiss. All the rock at this level is tillite, and then it's overlain by gneiss.
So this is the height to the top of the parapet wall in these panels. Yeah.
And what will they put, like a guardrail or a?
No, the concrete parapet wall.
That is the guardrail level.
Oh, okay. So the deck will be slightly lower than
that.
Okay.
1.2 meters down.
You don't need anybody hanging and doing a nosedive over the end of that.
Mm-hmm.
We've got harnesses on those guys. Are they connected? I can see the straps. The health and safety on site is.
We get audited twice a month. All those things are abided by.
Okay, while that's running, let me just go and see. There were a few more questions.
600,000 hours LTI free as well,
Yes.
which is quite a feat, especially at this high.
Yeah. Sorry, I forgot to mention that. 605,000 hours with no lost time injuries.
Okay, let me find the questions. Okay, this one is from give up, Mr. Umkhomazi. That's easier than the first name. Thank you for the presentation. And this is always, you cannot have a webinar, site visits, technical talk, anything. Do you provide? Sorry, the messages keep popping up. Do you provide vocation work to civil engineering students? If yes, are there available spaces and details? So I'm not sure to whom that question is generated, but I'll allow the contractor to answer.
Yeah, we do have internal programs with the company, especially the construction industry is booming at the moment, or we're coming out of our 10-year slump. So if you are interested, get a hold of Stephanie Stock's head office, and the HR department will happily.
So do they go to the Steph Stocks website and look up vacancies or whatever it is on the website?
I think if they can just pop into our head office in West Town,
okay.
I can
find site
and ask for help there.
Okay.
Entertained. But our site, we have brought some interns, postgrads through the ranks, and they are graduating to proper site.
You've not taken any of the students involved in the hydrological study to put them downstream, so if they fail.
No, we've got a lovely team on site. We've been grateful. So,
And then an extension from the same delegate is from the presentation, the chemically treated water won't go back to the river. What chemicals would be used, or I'm not sure if it will or it won't. What chemicals will be used to clean the water?
The polyelectrolytes, coagulants and flocculants. It's a polyamide, usually the whole basket of different chemicals you can use to destabilize the ions in the water, and essentially clay. Most of the content would be colloidal clay, which needs destabilizing so that it settle out.
You can see how clean the water is there.
Yeah.
That was taken yesterday. And those precast blocks behind the weir there are the steps in the fish ladder.
And vertical slots, like baffles in the baffles with a slot in it that the fish.
Then there's a question from Ian. Has security and vandalism been a challenge on site?
not so much security.
The site is quite remote, and there's no passing traffic other than the 2 people that stay beyond there. So I don't think it has been.
So it's going to take a serious effort to go and steal anything from the site.
Yeah, you've got guards at the entrance, so I'm sure that after hours, the people coming in there will be questioned as to why they are.
And it's quite difficult to steal a big block of concrete. So
if you're that desperate,
you can have it. In fact, you're not going to put a sign on the coffer wall to say, "Please take me," but you don't have to demolish it. Okay, let's see what else we've got here. Lots of comments on beautiful scenery and interesting project. Luke wants to know any problems with the construction mafia. I think you alluded to that, Gordon. What was it? The organized business forums, or was it just local interest groups that were your 2 months play around?
There have been issues, but they've been dealt with at a level higher than what we're sitting at here. And yes, that was part of the suspension and some of the early delays, but yeah, I don't think I'm really...
So the unfortunate Steph Stocks shooting on the 21st of June when I was running EP Clicky's site visit had nothing to do with your project.
I don't know.
Okay.
Probably not.
Because I think anybody wanting to go knock on the local office door may be second thoughts if you get shot at the gate. I'm glad to hear he's recovering. Okay, then the question from Shanae is, could you share some details on the staff team size and accommodation arrangements? And this probably again is directed at the contractor. Logistics must be quite a challenge in terms of the remoteness and location of the site.
We had at our peak, we had about 120 of our own employed labor. That was from general workers, shutter hands, steel fixers. That number excludes operators. There's probably about 20 operators there. And then our management staff's probably about 24, complement from site engineers to management, commercial side, as well as administration.
And is there a lab on site to do the testing of the concrete?
No.
How's that done? Commercially? And where? To Port Shepstone or?
No, it's coming to Pine Town.
Okay.
Contest is our contractor who's doing the testing for us.
Okay, and then look, this is, Gordon, you've partially answered this, but Peter Watt is asking, how did the contractor handle the issues arising from those site disruptions? And I think maybe you can give a contractor's perspective. You've given the amicable settlement via the GCC clauses.
That was one of them, but the employer has what they call ISD people, institutional social development consultants. And their function is to deal with community issues. They take it back to the employer, because really those are risks that are beyond the contractors. It's really an employer's risk, and they've been dealt with through various channels.
So the client has put into place most of the let's call it interferences to help both the design team or the consulting team and the contractor team.
Yeah.
Yeah. So you're not having to walk around with shotguns and guns.
It's a gun-free zone.
Okay, good. Nice to hear. Okay, then there's a question from Alan, your old sparring partner, Duncan. How thick is or was the reinforced concrete arch cofferdam? I think it's still there, so is the reinforced concrete cofferdam.
Isman can answer that. That was 800 wide.
I think the base is.
So it's tapers as it goes up.
And it's post-tension.
Oh, it steps.
A bigger base.
Okay.
The wall goes up.
Okay.
Then it's anchored into the
Rock anchor. Post-tension.
Okay. So when it gets demolished, the base won't get demolished because it'll just be within the river.
We have to take out what is downstream of the weir.
Okay.
Because that will influence.
What's going to be built downstream.
Yeah.
Okay.
Got to go back to the original riverbed, basically downstream of the weir.
Okay. Was a piling system used in the project? I don't think you've mentioned.
No.
So because of your rock being at a much higher level, your program in any case wasn't to go piling option. It would have been to excavate down and then backfill, but you didn't have to do that.
Being a high energy river, the bedrock in the river is pretty competent because over the years it would have eroded away. As it decomposes, it erodes away.
So yeah. I had one of the video clips, one that I didn't show. Inside the lower cofferdam wall, there was a little explosion, little blocks. And the reason that we did that is so that the peckers could get in on an edge to break it away, because it was so hard that they couldn't get in.
Okay. Okay, and then there's a comment, and I think I should almost disqualify this comment, given that Clive Rocastle used to work for Steph Stocks. But anyway, Clive says, congratulations to the contractor. Under challenging conditions, looks a very neat site with good quality concrete. So pat yourself on the back and
Thank you. That's nice.
yeah. You're going to get your bonus next year, Clive, so you can relax. Pumza, how difficult is it to adhere to the environmental compliance in this type of project, considering that the work itself is inside the river? Was there any VULA and all those other?
We've got VULA, we've got environmental authorizations, we've had amendments done to them. So yeah.
And has that created any time lags in terms of the project?
In the beginning, when we had a vegetation specialist investigations done, there was a short hold of it, it didn't impact the project.
And then with environmentalists always present us civil engineering types of challenges that on the one hand, when we were doing the design stage, they're saying, no, you can't build a weir, it's going to retain the sediment. We need the sediment to go down onto the coast, otherwise you're denuding the beaches. And we're saying, no, don't worry, it will sediment behind the weir, it's a low weir, it'll sediment up in the very first high flow, and then on the sediment will just wash over the top. And then we come along trying to do cofferdams and push earth into the river, and the environmentalists jumping up down and say, you're letting dirty water into the river, you're letting mud into the river, you must dam it off. We're saying, do you want the sediment or don't you want the sediment?
That's why you become an environmentalist, so you have the ability to change your mind frequently.
But again, we have environmental audits done twice a month. And they do it on the VULA and on the environmental authorization.
Okay.
And the contractors scored well over 90%.
And then there's a comment from Ian Schwartz, who says, very interesting, challenging project. Well done to all involved. So you can pat yourselves all on the back. Very challenging contract. Congratulations to the project team. And then the question from Brian, can the full material required be taken from the area which will be flooded after the project instead of importing? I'm assuming it's the full material between those where you showed the last end pictures, that those decks that you're going to. So the question is, can you use the material that's outside of the current construction to be put into there, or you're going to only import either from the sand?
It needs to be imported because the local material immediately by the next to the
Got a high clay
structures is high clay.
Okay.
So to
So,
cement stabilized sand,
so
you need proper
you've got
gradient.
a grading
Yeah.
requirement for that backfill material that you're going to cement stabilize.
But the contractor will be using it for his temporary works to build the north side of the weir in the next stage.
Okay, and then I think you may have answered this already, but Boyke commenters, was there any environmental outcry over the Coffer Dam earth washaways down the river?
No, there's a sand winning operation downstream, and
They
they're
were
very
grateful.
happy with anything that comes down the river. All it does is fill their pits.
And is
so
it
they're
a legal
happy.
sand operation?
It is illegal.
I must correct you. But there was an issue once when we were doing a lot of earthworks in the river.
You mean to do that demolishing work?
Correct. And obviously the farmers and the water users downstream monitor the storms. So when a storm's coming, they know they're going to have bad water. They didn't know that we were going to work in the river. So
the vegetable farmers, yeah.
We created an issue once. And then we created a WhatsApp group, and all those guys were on a WhatsApp group, and they were then told whenever something was going to happen. So they knew what to expect.
They could adjust
But
accordingly.
there's vegetable farming going on.
Okay.
They've got mono pumps pumping out
Okay.
the river in various places.
And then Wanda says, are any specialized materials, seeker swell and the likes as this, sorry, a message is getting in the way, is done in lift panels to prevent any leakages so as to attain a watertight structure? If so, are they done in-house by the main contractor?
No, only water retaining would be the low lift pump station, but the walls are already very thick at the bottom, 1.4 meters. So it's very easy to seal that. And it's only when it's under flood that you've actually got a hydraulic gradient, and hopefully the flood doesn't last long enough to manifest any leak. So the water stop type thing is the least of our concerns. The bulk mass gravity structure, it doesn't have to be watertight. It's 40 meters by 40 meters, 20 meters high, just as one big solid lump, and the water retaining is of no issue. Even the weir itself, even if it had minor cracks or leaks underneath, which is unlikely, that's of no real consequence, because you're not really, it's not a dam, it's just really creating a difference in water level.
And then Boyke, just so that the contractor doesn't feel left out, I know they get grumpy when they're left out. The question is, at what stage did the contractor figure out and budget or stroke price for all the massive temporary works?
When he tendered.
Yeah. So you mean the tender document was written in such a manner that there was no surprises with it? Well done to the project team. Okay, I'll come to the hand in a moment. I'm just making sure that I've got through all the questions. Lots of compliments to Duncan and Gordon and the team on site, so you can read those in the chat yourselves. Just making sure. There was a comment from Shavir. Great engineering design and implementation work. Do you perhaps have some financial indicators of the system rate of return or cost per kiloliter and how it compares to the expectations of the utility? So in other words, you know, your project cost versus what it's going to generate in terms of bulk water.
It depends on how you rate that, because
yeah.
if you look at the Inquidini system, the dam itself is 1.4 billion. The Inquidini extraction weir, which is still to be constructed, will be about another billion. So it's 2.4 billion straight away just to store water off season to release back in the river. And then we're spending about 1.6 billion on the good enough system to, on when they do the pipeline and reservoir, that'd be about another 500 million or so on top of the billion good enough. So and then the waterworks is going to be pricey. Like I think it was, I'm not quite sure what I think 8 billion. I'm not too clued up in what the tender rates were, but the waterworks is by far the most expensive component. So whether you include all of those aspects, it does make it rather dicky. But bottom line is you do need to augment the water resources in the whole Durban South Coast area. And economically, there's no other real way to do it other than desal. And desal is also desperately expensive, and where you're going to get the electricity from. So there's really not much option. The upper Umkhomazi, when it gets going, that's still many years away, but it's inching closer and closer to fruition. But that's going to be many years before the upper Umkhomazi can contribute to the whole Maritzburg-Umgeni Durban Metro corridor.
Okay. Charles, would you like to go ahead and engage? You can unmute Charles. There we go.
So, yeah, can you hear me?
Now we can hear you perfectly. Thanks, Charles.
Yeah, thanks, man. It's a very good presentation, and well done on the Stocks guys there. It's spectacular. I hope your cost reports are also spectacular for your sake. I asked a question which you skipped. This presentation, this recording of this presentation, will it be available to those of us who attended this the seminar?
Charles, as I said earlier to Gordon and to Duncan, what we do is I get it edited so that any technology challenges, etc., are chopped out, and then we upload it onto the SAICE YouTube channel. But if you pop me an email and you want it sooner, I will retransfer it to you, because it will probably be quite a big file. But you are most welcome to share. I don't think anything that Duncan and Gordon and the contractor have shared is top secret. At the end of the day, once the project is up and running, nobody will know about it. So it's good to have it in prosperity to see what engineers can actually do. So pop me an email. I'll put my email in the chat at the end of the session. But yes, we will upload it. It'll take our PR and marketing team a week or two to get it ready. They also will do the same with the ethics webinar for those of you that missed that this evening.
Thanks. I'll pop your email. Thank you very much.
You're most welcome. Anybody else? We are a little bit over our time now, which is always good for the CPD points, but we don't want to keep the team here indefinitely. Elaine, are you just commenting, or do you have to engage? My ICE colleague there, Elaine. You can talk to us, Elaine. Not going to talk to us. Okay, I caught him out, did I?
Hello, Tom. Thank you very much, everyone, for an excellent presentation. It reminds me of the heavy civil works I did in the Umgeni tunnels back in the late 90s. So it really is nice to see this happening again in KZN. Fantastic stuff. Thank you, guys.
Excellent. Danica, before you run away and deal with your clients in Dublin, any comment you'd like to make, as you were part of Duncan's team
The design
a couple of
team,
years
yeah.
back? Didi?
Can you
Yeah,
hear
I caught you. As
me
a
on
young
the spot
graduate engineer on the project, any comments you'd like to make about your experiences with the project?
Truly a privilege to have been involved in it. Very much appreciated, and it's really, really cool to see it coming to life. So well done to everybody there.
Cool. What you didn't know before we started streaming it was Duncan said anything that goes wrong, he's going to blame Danica for. So no, I'm teasing. He didn't say it. How's the weather in Dublin?
Sunny but chilly.
Okay. Yeah. Well, we're having Dublin Irish weather here in KZN at the moment. It's wet and miserable. Anyway, have a good evening, Didi. Anybody else like to engage with Duncan and Gordon and anyone else here before we wrap up the session? I guess not. So from the Academy's perspective and SAICE again, thank you to the GIB team and Steph Stocks and their partners, and obviously to Umgeni Utukela for allowing us to do the show and run the presentation. We're very grateful. Those of you that are attending and observing, if you have projects that you would like to also showcase, you know where to find me. If you don't know, then it's not difficult. I'll pop my email in the chat, and we're always looking for projects to be able to show the wonders of what we do as civil engineers and from a SAICE perspective in particular. But again, thank you to the design team and the implementation team, and to our contractor for delivery of such a nice project. Maybe we can visit again some early in 2026. I'm not sure Gordon, Duncan and I will still be alive, but the contractor will still be around. so that we can actually, we'll all be pushing 70 plus by then. We can go back and see maybe the end of the project and just see how it has come to pass. But thanks everybody. And